Hello, this is Jack Jackson. This video I want to look at the area formula for a trapezoid. We want to derive this formula and illustrate why it works, prove that it works. And actually, this is a very interesting problem because I know of at least 7 different ways of doing this, and there may be more. Um, so the idea here is we want to take a look at a general trapezoid. Now, we do have to be a little careful that it doesn't necessarily have to look just like this, right? So whatever method we come up with, it's got to be a general enough method so that when we look at other examples like the fact that these could have, one could have well, let's say if you started with a horizontal side, which you don't necessarily have to, but let's say we had one, then the legs, horizontal bases, you could have legs with, one positive slope, one negative slope. They could both have positive slope. You could have the base, this smaller base, completely over the bigger base. You could have it hanging out a little bit over here and not on the other side. You can even have a situation like this, and this is one you have to kind of be careful of when you're doing methods to see if they're going to work. You could have a situation like this one, where this base is completely separated from this base if you drew the perpendicular things there. Okay. So we're going to have to kind of look and see what we could do. So some of the things that people usually start to do may or may not work. Like just thing that kind of seems to occur to a lot of folks is, hey, just drop a perpendicular here and here. You got a rectangle and 2 triangles, add those up, that'll get you there. That will get you to the correct formula, but it doesn't necessarily work all the time for all, at least the proof doesn't always work. So for example, if you're looking at this case, say here, when you draw up the perpendicular, you get a triangle there, you get another, uh, you know, be a trapezoid ultimately there. It's a little bit, it's not clear exactly what kind of shapes you're going to get. Okay, so you have to be careful a little bit about that. So we're going to show you several methods that work no matter how we do it. The easiest method, I think, in the end is this first one that I'm going to show you. So we'll do method 1, and I'm going to slide you through the construction. Construct a diagonal from A to C. Now what do we have? Well, we just have 2 triangles, so it's pretty easy. We can just take these 2 heights, which are the same, the altitude from B down to here and from D up to here, same. This is base 1 is for this triangle, base 2 for this triangle. So this triangle has area, um, this one is 1/2 base 1 times height, and this is 1/2 base 2 times height. Different bases potentially, but the same height. So you can see the formula written that way, and it makes sense the way this formula is written because now this is an area of a triangle, that's an area of a triangle. Okay. Now, how about this method? Construct the midpoint of these sides. And then what you want to do is basically whichever way this looks, let's say it's looking like this, for example. Take this trapezoid on the top half, rotate it around point H until A is going to rotate to D. So rotate it 180 degrees or pi radians. And this is going to come down to here. This part's going to come down to there. Since this is a horizontal line, rotating 180 degrees will make it still be a horizontal line down here. And this line through this midline will rotate around and will be here too. So what is this length turn out to be? Well, this length down here is base 1 plus base 2. And this turns out to be exactly the midpoint of this top line segment here. So that's one of the things this does show you is that this midline is the average of the length of the 2 bases. But look what we get. We get a parallelogram. Okay. Or alternately, there's another ways to get this same thing without talking about rotations. For example, we could say just start here at D, go out a distance of B2, start at the midpoint, go out a distance of the average of the bases there. Those are going to be parallel, okay? And then finish this off. We're going to end up getting a parallelogram here. So at some point you need to somehow you have to prove that's a parallelogram. So let's see, what can we do? We could say, we can do it by rotations and show that it's a parallelogram. At least we have that's congruent. And this is congruent, so we have opposite sides are congruent there, and opposite sides are congruent here. That's a parallelogram. That's one way we can do it. Okay. But in any event, we get a parallelogram, and its height is 1/2 the height of the other the full trapezoid. So we get 1/2 height is the height of this skinny parallelogram, short parallelogram, and its base is base 1 plus base 2. So you could write the formula like that. See how it makes sense that way. All right, let's do another method, method 3. Again, find the midpoint, and then find the midline, and now just go down up and down perpendicular. Each one of these sides has length h, the height of the parallelogram. The height's the distance between these two parallel lines. And what do we get? We get a rectangle that has the same length, same area. How do I know it's the same area? Well, look at these two triangles. These two are congruent because this is chosen to be the midpoint. Okay, and they're right angles here. And we could either from parallel lines, this midline is parallel to the bases. We can see that a couple of different ways. And we get congruent triangles there. Again, you want to make sure this kind of, see if this method is going to work even in some of the weirder cases like this one here. Again, the part that's cut off here could go down here, and the part that's cut off here could flip up there, and you got a nice little rectangle. And you could write it like this. So what's the height of it? Well, it's just the height of the trapezoid, but the length of it, or the base of it, is the average of the two bases, the length of the midline. Okay, that was method 3. Here's method 4. Again, make the midpoint of the leg, construct the altitude. And this time we're going to rotate the entire trapezoid around here. So now what happens is this length A to B is down here. That's B2. This B1 goes up to here. And this piece here is congruent to this one. So now we see the big thing is a parallelogram. Okay, a few of these steps you might want to be sure you justify real carefully. But that turns out to be a parallelogram, but it's twice the size of the parallelogram we have in area. Okay, so what's the formula? Well, the base here is base 1 plus base 2, and then the height is h. So you multiply that together to get the area of the parallelogram, but then you need to do half of that. So you could write the formula that way. All these different algebraic formulas can be manipulated together to get from one to the next. You could write the formula that way, that way, that way, or now this way. Now, of course, those are the same algebraically. They better be if they're all going to work. But you could also see each one of them as being the area of some other figure. Let's keep going. Here's another one here. Say we have this here. Construct the midpoint of the leg again. And construct another leg, construct this one parallel to this one. So we got a parallelogram now like this. Okay, and what we do is we get a little triangle here, we cut that off and put it up here. And they get the same area. You have to prove that those two triangles are congruent. I think I've marked the parts that you know, so you should be able to see that that's enough. You may want to slow this down a little bit later and fill in some of the details of some of the proofs that I have. I got most of it up here at least. So what's the area of that parallelogram? What's base times height? Well, the base is here. Um, you can see once again it's the average of the bases is the distance across here, and that's the distance. Let's see. Do we have a parallel? Yeah, the parallelogram goes to here. And that's the distance across here is the average of the bases. And it's the same all the way up and down. So we got a parallelogram there. Half the length of the bases and half the, the average of the bases is your base, and then your height is still the height, h. Okay, let's look at another one. Okay, this one, the two bases were congruent. We have a parallelogram. Otherwise, we assume that, let's see, we want to assume that AB is the smaller one. That's the way I've got it drawn. Okay, then draw a parallel line here, and now it cuts it into a parallelogram and a triangle. So what do we get? The parallelogram has base 2 times the height, and the triangle, well, what's left for the triangle turns out to be base 1 minus base 2 is what we have. Okay, because we cut off, see, we cut off base 2 out of base 1. What's left is base 1 minus base 2 here in the height. Do some algebra on that, you'll see it's the same as the other formulas. All right, one more. This one, let's put it here where you can see it. Take a midpoint of a side and a vertex over here. Go from that vertex through the midpoint and go on out till it meets the parallel line here, the line going through CD, just extend it out. Okay, and basically cut this triangle off and flip it around and put it here. We can show that these two triangles are congruent. And now what do you end up with? You end up with one triangle there. So there are a whole bunch of different ways. Let's see, what is this one? The whole length here, you can show that this triangle here is congruent to the one up here. So this is base 2. So now the base is base 1 plus base 2. The height's still the same, h, so it's half of that. So you can see it as one triangle. You can see it as two triangles, uh, two triangles, one triangle, a short parallelogram for the same area, a rectangle of the same area, a bigger parallelogram with twice the area, a parallelogram with the same area that way, what are we doing here? A triangle and a parallelogram. We go there. If it was here, let's see, you want this one to work. You want this to be the longer side there. Okay, and then one triangle. So a lot of different ones. Here's some other things that are related to that. This one is has an animation. This is I think the last method I showed you. Take the midpoint of a side here and the vertex here, and then just basically cut the green part off and rotate it around. So here, this is nice because you can see the rotation going on. And then the area of that triangle. Okay, here's another one. That's a line. I think this is the same construction here. So you start with the trapezoid. Again, take the midpoint of the side, cut it down, make a triangle of the same area. This is another one here. This one doesn't find the area, but it's showing that if you take the this midline across here, you're going to be able to get, it's going to turn out to be parallel, or just draw a parallel through it, show that it has to go through the midpoint of the other side. Okay. And then, of course, then the way you could do the area is cut that off and bring it over here. So that gives you a parallelogram. That's one of the ones we looked at. Here's another one. So again, this is the same one that we looked at a while ago, except now we're going to go a step further. You could not only take that, you could flip it over and make a parallelogram that way, and you could even turn that into a rectangle. So there's another rectangle, I think different than this. May be another one that I didn't have, where it's half as tall, but has the right base there. Okay, so it's 1/2 h times parentheses b1 plus b2 close parentheses. That may be one I missed. Okay, so yeah, there's lots of cool ways of getting areas of trapezoids, and in the end, what is the what do we have? So this one, let's see, this is another discovery about the median of a trapezoid. Watch this. If you take this at this point right here and rotate it around, you get a parallelogram. That's one way we got the area. Okay. Another way we could do it here is just noticing that this is noticing that it's parallel. So the median has um, um, a length the same as the average of the two bases, and it is parallel to both bases as well. So that's kind of a nice property of that trapezoid as well. So we ended up with lots of cool formulas. Let's see if I can get back to. Let's see, what does this one do? Yeah, we looked at this one a while ago. Where's the one? Yeah, here's the one I had. So look at the formulas. There's one way. There's another way. This is probably something like this is the way I would write the formula normally. 1/2 times h times b1 plus b2. Or that way, h times the average of the bases. I probably think of the formula this way. But all of these ways of writing the formula are the same. Another way to think of it, half the sum of the bases, base lengths, and then times the height. That's a more complicated way to write the formula, but it does, you know, do the algebra, multiply the half, combine like terms, and so forth. So that is the area of a trapezoid. Pretty interesting, huh? You wouldn't think that that would have so many different possibilities there, but it does. And maybe there's more. Lots of cool stuff there.